So let me explain what Kennard and Weil made out of this uncertainty paper. So their version is something that I call preparation uncertainty. Scenario is very simple. So I have two kinds of measurements, let's say P measurement and a Q measurement, momentum and position. And I measure that in the same state. Right? So both observables are measured in the same state. And of course, this gives a distribution, right? This gives some histogram, I don't know, I don't care what it is, something like that. And so this is the experimental outcome where I fix the states and I make the position, the momentum measurement and the position measurement. And then the delta P, sort of in the state, let's say, to be more explicit, I would put the state in the as an index to this delta symbol, is expectation of variance of that distribution, which would do like that. Right? So the second moment minus expectation, and you take the standard deviation. So something like that, right? And so that's what you learn in school, right? Or in university. And so this is similar expression for the delta Q. And that's the interpretation. This is the operational interpretation. And so you know exactly how to measure delta P in a certain state and how to measure delta Q. And then the conclusion is, the theorem then is for all states, delta Q is h bar over 2. So this is what you learn in basically every quantum mechanics lectures. So let me draw a picture for this. So what you're actually doing is you have a fixed state, and for every state I get a pair of numbers. Let's say the delta P number and the delta Q number. Actually, it's probably better to look at the variances. Right? So anyway, but the same quantity. It's just a rescaling of the axis. So let's look at this diagram. So I come up with one state. Will give us a dot. Okay, we get more dots. And then there's a certain region that you can fill like that, right? So this is the set of possible pairs of delta rho P, well, actually, Q delta rho P, right? X-axis is first. So the statement of the uncertainty principle really is that is about this. There is white space at the bottom. So around the origin, where both would be small, you don't find a state that does that. That is the basic statement, right? Now, there are different mathematical relations that would express that. And this thing with the products is just one of them. You could just as well look at a linear combination of the two variances and say that maybe there's nothing below this line. Well, that's supposed to be a straight line, right? There's nothing below this line. That would be a sum of variances that is constrained. And that would have the same conceptual meaning, right? So the important thing is to say that you cannot make both small, and there are universal bounds that don't depend on the state. That's the whole point, that they don't depend on the state, that tell you cannot make both small. Right? So this is the idea of uncertainty. Now, in this generalization, you can immediately exchange P and Q for anything, right? So any observable that you could come up with, you can investigate with such a diagram, right? So you can draw such a diagram, you can do your inequalities. That may be hard work, but well, so for example, for angular momentum, you would get something similar, right? So you know, we have a spin 1 representation, and you look at the two components of the angular momentum. Then you get a diagram like that. Well, actually, as long as in finite dimensional quantum mechanics, which is much of quantum information is about, this product form is really bad, because we are looking for state-independent lower bounds, right? So this is the whole point here. This is the state-independent. So, in the finite dimensional situation, this best state-independent lower bound is zero if you look at the product, because you have eigenstates. So if you know this Robertson relation, which is sometimes sold as a generalization, well, it's a true relation, but it's not an uncertainty relation, right? Because it doesn't have this state independence property. It doesn't tell you that there is white space at the bottom. You cannot conclude it from that. So you have to work again. And so for example, you could look at the paper we did on the angular momentum uncertainty. But okay, but this is one way to make it precise, right? So this is a particular scenario. And if you look in Heisenberg's paper, then this misses out on almost everything that Heisenberg says. It's true, it's a very useful general principle, but when you read Heisenberg, he discusses the microscope wave, approximate measurement of position, and that messes up the momentum or something like that. So in this experimental setup, no particle ever sees both the P measurement and the Q measurement. In Heisenberg's microscope, that is definitely the case. Right? We look for the same particle, we look at position and momentum. So it's a different sort of scenario. And so one solution that many of my colleagues used is proving this one because it's easy, and claiming that they've actually proved the other thing, that you, for example, that you cannot measure position and momentum jointly, which is simply not what the proof says. Right? So the real topic of this talk is, how do I get this right? Right? So how do I bring the other side, the measurement side, in and explain in operational terms what uncertainty relations should be for that kind of problem? And that's my next topic.